Welcome to the last class, to the last lecture, I mean. Before I start with the review, I just want to finish the last couple of remarks about chapter 42. And as a reminder, we left off with talking about nuclear fusion in the sun. And we have the weak interaction turning protons into neutrons and then producing hydrogen-2 or deuterium. And then you make helium-3 out of that by attaching another proton, and two helium-3s fuse together to combine to helium-4 and two protons. And that is how most of the energy is produced in the sun. And the sun also produces heavier elements by fusing those helium-3s with the finished product helium-4 to get beryllium-7, lithium-7, and boron-8. Other stars than the sun, hotter stars, they prefer a different process, which is a catalytic process, the so-called CNO cycle. And you start with carbon-12, and you successively attach protons to it. And every once in a while, you get a beta-plus decay that turns them into neutrons. And at the end, an entire helium-4 pops out when you attach the last proton. So that's a different way of producing energy in the hotter stars. And finally, the older stars, which have exhausted their hydrogen supply, they can fuse helium-4 nuclei, 3 of them, to form carbon-12. That doesn't happen in the sun because usually this intermediate state, which is beryllium-8, is very, very short-lived, so it requires a large density of helium-4s to make sure that the third one hits in time before this one breaks apart again into two alpha particles. The experimental evidence for this nuclear fusion process are the solar neutrinos, because there are two neutrinos coming out of this PP chain or the CNO cycle. One can actually measure the different types of solar neutrinos, and these are the energy spectrums in the log plot. So the predominant one is this first process that turns protons into neutrons. And 3 of those have been uniquely identified. And for that reason, we know that indeed nuclear fusion processes happen in the sun. Unfortunately, so far there's no observation of the CNO neutrinos, which are those yellow ones. Because that would prove that this other process exists in stars as well. One can try and reproduce nuclear fusion processes on Earth because one can produce a lot of power that way in principle. Unfortunately, weak interaction processes, one has to wait for a very long time or acquire a large amount of fuel for this to happen efficiently. And large amount means typically the size of a star. And so a more reasonable nuclear reaction is the fusion of deuterium or hydrogen-2 with tritium or hydrogen-3 into helium plus a neutron. So also in stars, to get past the Coulomb barriers, one uses the thermal energy of the particles, and that means that the matter gets so hot that it goes into the plasma state where the atoms are completely ionized. And for that to stay that way, the plasma has to be confined. If it's in thermal contact with another material, then it either will destroy that material or it will reneutralize and stop being a plasma. In the star, the plasma is confined by gravity, and on Earth we can try and use magnetic fields. Another possibility is to use inertial confinement. And that means that you produce high enough densities and temperatures for a short period of time, and then all fusion processes happen in that short period of time, and then the plasma falls apart. And an example of that are nuclear weapons. The H-bomb uses that. It uses a conventional nuclear bomb to produce and ignite the plasma. A less violent way is studied at the Lawrence Livermore National Laboratory at the National Ignition Facility, where one tries to use lasers for a more controlled process of this type. And finally, one can use accelerator beams to overcome the Coulomb barrier. For example, one can buy relatively cheaply Deuterium-tritium fusion generators that produce neutrons. They're useful for finding oil deposits in the Earth, for example. And they make the same process. So let me now summarize this chapter. So this chapter was all about ionizing radiation. Ionizing radiation can damage material and, in particular, biological tissue. And we use the unit of becquerel or curie to measure the source activity. And 1 curie is 3.7 times 10 to the 10 becquerel. And 1 becquerel means 1 atomic disintegration per second. More relevant for damage is the unit of gray or rad, which measures the absorbed dose or the energy deposit. 1 rad is 0.01 gray, and 1 gray is 1 joule per kilogram of mass. And finally, for biological damage, what is most relevant is the effective dose, since different types of radiation damage biological tissue in different ways. And so one multiplies the absorbed dose by a quality factor, which depends on the type of radiation. And the unit then is rem, or sievert. Rem stands for Röntgen equivalent man. 1 rem is 0.01 sievert. 1 sievert is the quality factor times 1 gray. And effective dose of 10 sieverts is usually a death sentence. So nuclear radiation has beneficial uses. For example, one can use it to cure cancer. One can also use nuclear processes to study biological structures and for medical diagnosis. In the tomographic imaging techniques, one uses multiple angles to reconstruct images of the human body, for example, in CT scans, positron emission scans, single photon emission tomography, and magnetic resonance imaging. And the magnetic resonance imaging uses the nuclear magnetic moments and the resonance that occurs there. So nuclear reactions include, among other things, other than decay, nuclear fission and fusion, and it can produce new isotopes and elements. And finally, solar neutrinos demonstrate that the pp chain, the fusion of 4 protons into helium, is what powers the sun. Let's now review the rest of the class, and I start all the way at the beginning. We started our journey with the discussion of simple harmonic motion, and a typical example of simple harmonic motion is mass and a spring. And the important part is that the force is not a constant like in other processes. So the force is proportional, it's not a constant, but it's proportional to the displacement. And there's a spring constant K that is this proportionality constant. So the resulting motion is a sinusoidal motion like so. And we can define the period, which is the distance between successive minima or maxima, or the time of one cycle. The frequency is the inverse of one cycle. The amplitude is the amount of the maximal deviation or displacement from the equilibrium x0. And the phase is the distance between the first maximum and the origin. And we describe this mathematically by this: x equals x0 plus a times cosine omega t plus phi. Omega is the angular frequency, which is 2 pi times this frequency here. And omega square is given as the ratio of k over m, where k is the spring constant and m is the mass. And a and phi depend on the initial conditions, meaning what is the displacement at time equals 0 and what is the velocity at time equals 0. So the energy in simple harmonic motion is the sum of the kinetic energy, or 1/2 mv square, plus the potential energy, 1/2 k x minus x naught square. And it changes back and forth between kinetic and potential energy. So the energy is traded back and forth, but this total energy always stays the same. Another system that undergoes simple harmonic motion is the simple pendulum. There the resonance frequency, or the angular resonance frequency, omega square, is given by the ratio of the constant of gravity over the string length, and it does not depend on the mass. Friction leads to damped harmonic motions, and the most interesting case is the underdamped system, where we get something like the simple harmonic motion, but the amplitude is modulated with an exponential factor, meaning that the amplitude decreases exponentially. There's also critical damping or overdamping, but there no oscillations occur at all. If an external force is applied to the oscillating system, then the amplitude can get very large if the frequency of that force, if it's periodic force, is close to the natural or the resonant frequency. And therefore this phenomenon is called resonance, and larger damping leads to a broader resonance curve. So let's move on to wave motion. First of all, such oscillating systems, as we just discussed, act as sources of waves which can propagate through space, for example as sound waves, or in systems like a taut string. One can transmit single pulses or continuous sinusoidal wave trains. We define, in addition to the frequency and to the period, we define the wavelength, and that is the distance from wave crest to wave crest. Then, of course, we still have the amplitude A, and the wave velocity, meaning how fast are the wave crests propagating, is given by the product of frequency and wavelength. Waves can be transverse or longitudinal. In a transverse wave, the oscillations of the particles in the medium are perpendicular to the direction of propagation. And in a longitudinal wave, it is parallel. Waves transport energy, and the intensity I, or the power per area, is proportional to the square of the amplitude. And for three-dimensional waves, the intensity decreases with the square of the distance, and the amplitude decreases linearly. One can also define the wave number, which is 2 pi divided by the wavelength, in a similar way that the angular frequency is 2 pi divided by the period. And don't confuse this k with the spring constant k. And in a sine wave, one mathematically describes the wave as displacement as a function of both space and time. So the amplitude A times sine of kx plus or minus omega t plus phi, or k parentheses x plus minus vt, where v is the propagation velocity of the wave plus phi. And waves that pass through the same region of space at the same time, they add. That's the principle of superposition. And this is also called interference, and it can be constructive, destructive, or partially destructive. And if waves encounter objects, they reflect off those objects, and the angle of reflection equals the angle of incidence. That's the law of reflection. And when the wave encounters a boundary to a different medium, then it can either reflect or refract, and the refraction is a change in direction, and it originates because of different wave speeds in the two media. And the law of refraction is that the ratio of the sines of the incident and refracted angle equals the ratio of the phase velocities. And finally, there is diffraction when waves encounter obstacles, meaning that the waves seem to flow around those obstacles. And the angle of that direction change is approximately the wavelength divided by the size of the object. Waves can interfere with their own reflections. If that happens, then usually standing waves are produced. And these appear as vibrations, but that is no sense of motion in the standing waves. There are several such modes of vibration, and mode just means a particular manner or particular pattern. Each mode has its own resonance frequency. The lowest of those is called the fundamental, and the others are called the overtones, and all are sorted and labeled as the nth harmonic. The pattern are typically defined by nodes. Those are regions that show no vibration at all, and antinodes, those are regions that show maximal vibration. And if you have a chord of length L fixed on both sides, the wavelength of the nth harmonic is twice the length divided by n, where n is a positive integer. And the frequency is n times the velocity divided by twice the length. So the first wave that we studied was sound, and sound, first of all, means both sensation in our mind and the physical phenomenon that is the cause for that sensation. Sound waves are longitudinal waves, and sound is transported in air or in other materials. There's the sensation of pitch, and that is related to the frequency. And the audible range is between 20 hertz and 20,000 hertz, or 20 cycles per second to 20,000 cycles per second. The sensation of loudness is related to the intensity. The loudness is actually proportional to the logarithm of the intensity, not to the intensity itself. And one therefore defines the sound level, beta, as in units decibel, 10 decibels, times the logarithm of the ratio I, where I is the intensity, and I naught is some reference intensity, which is taken as the human hearing threshold, or 10 to the minus 12 watts per meter square. And the sources are vibrating objects. Typically standing waves are produced, and then those vibrating objects, they originate traveling waves. And the rule is that the frequency in the air is the same as the frequency in the object, but the wavelength in the air doesn't have to be the same as the wavelength of the object. The fundamental wavelength of strings and open air tubes is the same. The fundamental is twice the length. Odd and even higher harmonics exist if the tube is open on both sides. If the tube is closed on one side, then the fundamental wavelength becomes twice as long, 4 times the length, and only the odd harmonics exist. So the wavelength of the nth harmonic is lambda 1 over n, and the frequency of the nth harmonic is f1 times n. So that's the same as for the string. There's the so-called Doppler effect, which changes the pitch of sound if the source or the listeners are moving, and it's described by this formula, which encompasses all such cases. And one needs to take care of getting the proper sign for the listener. If the medium moves, for example, one has wind, one can reduce that motion, assuming that the source, by changing the motion of this source and listener. Because of the principle of relativity, one can always add a constant velocity to all 3 parts of the system, meaning listener, source, and medium. Objects that move faster than the sound velocity emit shock waves, so-called sonic boom. And sonars and medical imaging devices uses ultrasound echoes to determine distances to objects and their speed. So the next wave that we encountered was electromagnetic waves. And those are governed by Maxwell's equation. And that is the culmination of 19th century physics. And there are 4 Maxwell equations. The first one is Gauss's law for the electric field, meaning that the electric charges are the sources of the electric field. And Gauss's law for the magnetic field is that there are no magnetic charges. Then Faraday's law states that a changing magnetic field or flux induces a circular electric field. And Ampere's law states that a current or a changing electric field or flux induces a circular magnetic field. Maxwell's equations predict transverse electromagnetic waves emitting from charges if those charges are accelerated. The propagation speed is given by this equation, c² times mu naught times epsilon naught equals 1. And that, if one plugs in the number, gives us a propagation speed of 3 times 10 to the 8 meters per second, which is also the speed of light. For plain sinusoidal electromagnetic waves, one can relate the electric amplitude E naught to the magnetic amplitude B naught by the speed, or the speed of light. And electric and magnetic fields are perpendicular to each other and perpendicular to the direction of propagation, which means that electromagnetic waves are transverse waves. There is a very large electromagnetic wave spectrum, meaning many different frequencies or wavelengths. One can define a Poynting vector, which is the cross product of electric and magnetic field over mu naught, and that gives the intensity of the electromagnetic wave. Light is one type of electromagnetic wave of a particular wavelength, typically on the order of 500 nanometers. Electromagnetic waves carry momentum as well, and they exert radiation pressure, and electromagnetic waves are central in human communications. We studied the reflection and refraction of electromagnetic waves and in general, and light in particular. So in general, a wave slows down when it propagates in a medium. An electromagnetic wave slows down when it propagates in a medium. And the amount of slowdown is characterized by the index of refraction, meaning that the propagation speed is the speed of light in vacuum divided by the index of refraction. And just like for all waves, we have the law of reflection. The reflected angle equals the incident angle. And one can use that to make plane mirrors, which make virtual images which are always upright and the same size as the object. Or one can make spherical mirrors of a curvature radius r, and those have a focal point, meaning that reflections from parallel rays are reflected to meet in this focal point. And the focal length is given by the radius of curvature, or by half of the radius of curvature. And one distinguishes the concave mirrors where one assumes that this radius is bigger than 0, and the convex mirrors where it's smaller than 0. And concave means the mirror looks like this, where the light hits from that side. And convex means that it curves the other way. One can construct ray diagrams. Focal rays reflect parallel concentric rays which seem to go through the center of the sphere, reflect on themselves, and center rays reflect as if it was a plane mirror. And with the ray diagrams one can construct the image, or one can also use the mirror equation, which relates the object distance dO to the image distance di to the focal length. And once one has those distances, one can determine the magnification of the image with respect to the size of the object. So that is the size of the image, that is the size of the object. A real image emits real rays, and a virtual image just appears to be the location where rays are emitted, but no rays are actually coming from that point in space. Convex mirrors only make virtual images that are smaller than the object. Then we encountered the law of refraction again. So this ratio of sine is related to the ratio of phase velocities, and therefore the product of refractive index and sine stays the same when refraction happens. Light of wavelength lambda entering a medium with an index of refraction has a reduced wavelength, like so, and the frequency doesn't change. The light frequency determines the color, but the wavelength in air is used to describe it. So 400 nanometer means violet, and 750 nanometers means red, and in between is the visible spectrum. The index of refraction depends on that wavelength, that is called dispersion. And if the index of the refracted medium is smaller than the index of refraction in the incident medium, then total internal reflection happens. If the angle is bigger than the critical angle, where the critical angle is defined by this equation. So we moved on to lenses and optical instruments. And lens uses light refraction to image objects. And like the spherical mirrors, there's a focal point and a focal length. And one distinguishes the converging lens from the diverging lens. So converging lenses are described with a positive focal length, and diverging lenses are described by a negative one. And that corresponds to the concave mirror and the convex mirror. Be careful, the converging lens can be convex or concave. It depends on the index of refraction that is used. The lens power is defined as the inverse of the focal length, and one can get a lens equation very similar to the mirror equation, which relates the focal length and the object and the image distance. And the magnification equation is also the same as for the mirror. And one has to make sure that the signs in this, for those pieces in this equation are evaluated correctly, otherwise the equation will give you the wrong answer. So one can do the ray tracing similar to spherical mirrors, and the lens maker's equation relates how to get the focal length from the index of refraction and the curvatures. Cameras use lenses to image, and the focusing is done by moving the lens with respect to the film to make sure that the image distance corresponds to the distance between film and lens. The brightness is adjusted by the f-stop, the focal length over the diameter of the lens, and the shutter speed. The eye doesn't have a shutter. It focuses an image on the retina by accommodation, meaning that the curvature of the lens is adjusted. And one can use converging and or diverging lenses or even cylindrical lenses to correct defects in the curvature of the eye, which is called astigmatism. A magnifying glass is a simple converging lens which forms a virtual image if the object is at the focal point. And the magnification one can get from such a simple object is the near point divided by the focal length. And the near point for the normal eye is 25 centimeters. In an astronomical telescope, one has an objective with focal length FO, which can be a lens or a mirror, and an eyepiece or FE to view the image of the objective. So one has to trace two images. And the total magnification is roughly the near point times the length, which is the distance between eyepiece and objective, divided by the product of the two focal lengths. Then finally, there are defects of lens imaging called aberration, and that limits the sharpness of images, and some can be corrected for. We looked at the true wave nature of light, and we started with interference phenomena. The wave nature of light is apparent in either the interference or the diffraction of light. And the Huygens principle states that one can assume that every point on a wavefront is a source of a spherical wavelet. And then the next wavefront is constructed as the envelope of those wavelets. Wavelengths of light in a medium with index of refraction n is reduced, as we discussed before. And the first demonstration of interference is the Young double-slit experiment. And in that double-slit experiment, constructive interference occurs if the angle under which it is viewed, theta, if the d times the sine of theta equals an integral number times the wavelength. And this integral number can be 0, 1, 2, 3, 4, until you hit the 90-degree boundary. And destructive interference occurs when you get m plus 1/2 lambda. Two sources of lights are coherent if they have the same frequency and maintain the same phase relationship. And interference can only be observed if the light is coherent. So interference can also occur between reflections from the front and back surfaces of a thin film. Light undergoes a 180-degree phase change if it reflects from a medium of higher index of refraction. We then moved on to diffraction, and that means that light bends around obstacles, and it produces a diffraction pattern, and that diffraction pattern has also constructive and destructive interference. And the easiest example is a narrow slit, single slit, of width d, and you observe a bright, wide central maximum, and minima for the condition sine theta equals m lambda over d. And don't be confused, that is the same formula as for the maxima of the double slit experiment. But in this case, m can be plus minus 1, 2, and 3, but not 0. Because 0 is actually the bright white central maximum. The wave nature of light actually limits resolutions of optical instruments, and the Rayleigh criterion demands that is derived from the circular aperture, which has a slightly different condition for the first minimum as this one. It's 1.22 lambda over d, where d is the diameter of the circular aperture. Therefore, the largest useful light microscope magnification based on this Rayleigh criterion is 600 times. If you magnify more than that, then all you will see is the interference pattern from the diffraction. One can use multiple slits as well, and then both the diffraction and the interference between the different slits is observed. And in the extreme case, you get a diffraction grading where you have many slits next to each other. If one makes the slits narrow enough, then one just produces a very sharp and bright maxima of equal brightness. And the condition for those maxima is given by these. And in between, it is just dark, so there are no true positions of minima. The diffraction gratings are used, for example, in spectrometers to separate and measure different wavelengths. For example, the line spectra from the different elements. X-rays are also electromagnetic waves, and they have shorter wavelengths, and they are produced by collisions of high voltage accelerated electrons with glass or metal targets, useful to study the crystal structure of materials, for example. And they played a role in the discovery of the double helix structure of the DNA. Light, since it's a transverse wave, also has the phenomenon of polarization. Unpolarized light means that the electric field vector is, of course, perpendicular to the direction of motion, but it has freedom. If you have a light beam that goes like that, electric field vector can oscillate this way or diagonally. And then it's unpolarized when there's no preference for any of those. It is called plane polarized if the electric field vector oscillates in one plane only. And then you can either have horizontal or vertical polarized, or this way diagonal and that way diagonal. Unpolarized beam that passes through the Polaroid sheet becomes polarized. If you have two Polaroids, the first one acts as the polarizer and the second one is then the analyzer. And the transmitted intensity of the second one is the intensity after the first one times the cosine square of the theta of the angle between the two Polaroid sheets. The reflected light from an optically thinner into an optically denser medium becomes also polarized. And 100% polarization is observed with the polarizing angle or Brewster angle, which is given by the tangent of theta p equals n2 over n1. Where those are the indices of refraction. We then moved on to modern physics, or in particular quantum theory. And quantum theory starts with Planck's quantum hypothesis explaining the blackbody radiation spectrum. So molecular vibration energy is the hypothesis that it is quantized in units of hf, meaning that you can have not any energy, but just an integral number times h times f. And f is the frequency of the light, and h is a new constant discovered by Planck. And Einstein suggested, as a consequence, a particle theory of light, that light consists out of particles called photons, and a photon has the energy hf and the momentum h over lambda. And this explains the photoelectric effect and the Compton effect and electron-positron pair production. Light has therefore a dual nature of both particle and wave. And de Broglie then suggested that particles like the electron should also have wave properties. And the wavelength of the electron, for example, is given by h over p, where p is the momentum of the electron. And this led to the development of the electron microscope. In quantum mechanics, the principle of complementarity demands that one needs to take into account both the particle and wave aspect of either light or matter to fully understand it. And the experimental setup will decide if the wave or the particle nature of light or of matter is revealed. Early scattering experiments revealed that the positive charge of atoms is concentrated in a small nucleus of the atom, which is surrounded by a cloud of electrons. And the Bohr-Sommerfeld model is a model of the atom that has electrons orbiting around the nucleus like a miniature solar system. Standing electron waves on those orbits with the de Broglie assumption of the wavelengths explain why only certain energies and angular momenta are possible. And the quantization of energy can be summarized by this formula, where this is the ionization energy of hydrogen, this is the charge of the nucleus, and this is a positive integer number. And this model explains the atomic line spectra. We then moved on to nuclear physics and radioactivity. And nuclear physics studies the atomic nucleus. Those nuclei are made out of nucleons, which in turn are made out of smaller things called quarks. Protons have the charge plus the elementary charge, and neutrons have no charge. The nuclide X is characterized by the number of protons and the mass number A. One writes symbolically AZX, and A is given in the unified atomic mass units. 1 U is 1 gram per mole, and it's equivalent to the energy, or the energy over c square of 931.5 MeV over c square. In kilograms, it's 1.66 times 10 to the minus 27 kilograms. The nucleus is held together by the nuclear force, and that is a residual effect of the attraction between quarks. And that attraction is governed by a new charge of a new interaction, the strong interaction. And that charge is referred to as color. The mass of the nucleus is less than the sum of the constituent masses, and the difference is made up by the binding energy. And the binding energy per nucleon is approximately 8 MeV, and it can be used as a measure of the stability of the nucleus. The nuclear force has a short range, only a few femtometers or 10 to the minus 15 meters. And the nuclear radius is proportional to the mass number to the 1/3 power, which means that one can picture nucleons as hard spheres that do not penetrate each other. Nuclei can be unstable and undergo radioactive decay. Then they change into other nuclei and sometimes emit particles in the process. The alpha decay emits a helium-4 nucleus, so 4 nucleons together, and it is governed by the strong interaction. Those alpha particles tunnel through the Coulomb barrier in violation of classical physics. This is a quantum mechanical effect. Beta decay emits positrons or electrons and a neutrino. It is governed by the weak interaction. And gamma decay emits photons or gamma rays, photons of very short wavelength, to de-excite the nucleus, meaning make it lose some of its extra energy. And it's governed by the electromagnetic interaction. The nucleus itself is not changed, it just changes from the excited to the state to the ground state. The transformation of parent to daughter nucleus is called transmutation. And all these decays conserve energy, linear and angular momentum, electric charge, the so-called baryon number, which you can think of as the number of nucleons, and lepton number, which is the number of neutrinos and electrons. The time behavior of the nuclear decay, one can understand that by a proportionality of the number of decaying nuclei, delta n out of n, that exist in the time interval delta t, so it's proportional to both n, the total number of existing nuclei, times the time period. And that leads to an exponential decay law, and one can then define the activity or the rate as the time derivative, and that activity also obeys an exponential decay law. One defines the half-life as the time required for half the nuclei of a sample to decay, or for the activity to die to 1/2 its original level. And this half-life T1/2 is correlated to the decay constant lambda, or the mean lifetime tau, by this factor 0.693, which is the natural logarithm of 2. Radioactive decay is useful for dating materials, for example, using carbon-14 or the uranium decay chain. There are detectors to detect radiation, for example, Geiger counters, photomultiplier tubes, scintillation counters, semiconductor detectors, and the first one ever used, photographic emulsion. And some of those are able to track charged particles, for example, the cloud bubble chamber, the photographic emulsion, drift and time projection chambers, as well as semiconductor trackers. And then, of course, lastly is what I just summarized at the beginning, that radiation can cause both damage as well as being useful in medical science. With this, I think this class is finished, and I see you at the front.